So, today's lecture is physical properties of seawater. There are basically 5 parameters to be discussed. First one is pressure, then temperature, then heat. Temperature is obviously associated with heat influx, and salinity and density. Now, the first you can say that the pressure. Now, in pressure is actually force per unit area. And normally in CGS or MKS CGS units, these are given in dynes per centimeter square. Or it is measured in pascals, so which is nothing but 1 Newton per meter square. Now, pressure in the ocean. So, ocean pressure is denoted in decibars. So, this is the unit of pressure by which oceanographers are familiar. So, it is denoted by decibar, and 1 bar is, that is your 1 atmospheric pressure. So, this is equals to 10 to the power 6 dynes per centimeter square. So, this is 10 to the power 5 pascals if you work out the numerics. So, this is 10 to the power 5 pascals, and this is your atmospheric pressure. Atmospheric. Now, variation of ocean pressure. So, this is varies from near zero at ocean surface to 10,000 decibar. So, this is 10,000 decibar. This is in deep waters. So, this is the variation of pressure. So, you can see 10,000 decibar will be at around depths of say around 10 kilometers depth, at say 10 kilometers depth of ocean. So, whenever you are engineering any object down below the, especially in the deep waters, you have to take account of this huge pressure. So, our order of 10,000 decibar means 1000 times atmospheric pressure. So, that is 1 decibar is 10 to the, yeah, I think roughly it is 1/10 of an atmospheric pressure. So, that is why actually for this large depths of 10 kilometers, we are as yet, I mean most of the countries have not yet developed a submersible to go down to this large depth. Submarines can go at best 1 or 2 kilometers down, but this kind of handling of tremendous pressure is itself an engineering feat. Now, this is so far this is your vertical. There are 2 types of pressure. One is the vertical pressure gradient. And the other is the horizontal pressure gradient. So, what are these two types of gradients and what do they do? Now, your vertical pressure gradient, so that is, most of you are familiar with this. It is your vertical pressure gradient. Gradient means the difference in pressure over a finite depth or a finite horizontal spread or horizontal distance. Now, vertical pressure gradient is what? There is difference in the vertical pressure is your hydrostatic pressure, which with you are most familiar. This is the hydrostatic pressure. So, the difference in the gradient is a difference in pressure, or sometimes this is called pressure down. In oceanographic terms, we say force is directed down the pressure gradient. So, that means wherever we have difference in pressure, we have a force. So, force is directly proportional to the difference in pressure or directly proportional to pressure difference. Now, there are two types of force. One is the balancing your hydrostatic pressure, that is your, that is, so force is directly proportional to, so what does this force do? It drives ocean flows. Ocean flow is driven by this force, which is directly your difference in pressure. Now, there are two types of flows that you will find. One is a this vertical flow or vertical force, another is a horizontal force. So, from the pressure we will get these two types of forces. One is the vertical force and the other is the horizontal force. Now, this vertical force, you will not find great flows taking place in the vertical direction. So, vertical force actually balances the force of gravity. What is this force of gravity? That is the weight of the water column. So, net force in the vertical direction is somewhat 0, is more or less equal to 0. So, there is no flow in the vertical direction. So, vertical flow is hardly present. Or vertical flow in ocean is hardly present. and this phenomena is called hydrostatic balance. So, your hydrostatic pressure is what? Hydrostatic pressure, all of you should know, this is equals to rho GH. So, this is actually supporting the water column or water mass. So, hardly you will get any flow in the vertical direction. So, this is called hydrostatic balance. Now, in the vertical direction, this is hardly for just for your knowledge. So, a pressure change of 1 decibar, that is 1/10 of a bar, occurs, this is over a depth change. Over a depth change of slightly less than 1 meter. This is the numeric if you have a vertical flow. Now, coming to the horizontal flow. So, horizontal pressure gradient. So, obviously, the flow will only take place if there is a difference in pressure, difference in the pressure or force. Now, horizontal pressure gradient. But as you can see from this note, you still have a pressure change over a depth. Although it is balanced, you call hydrostatic balance, but still there is some force there in the vertical direction. Now, horizontal pressure gradient drive horizontal currents, or you can write drive horizontal flows. Now, this is due to variation in mass distribution. In mass distribution of water. So, that is where water is more dense, it will try to displace the less dense water. So, normally actually in oceanographers, water masses, the oceanographers, they identify water masses with a defined pressure. This is a defined pressure, or sometimes they say it depends, because pressure depends on density, it also density. So, that is you have to segregate and demarcate various water masses flowing in the ocean, and this is done by marking particular water masses with their characteristic pressure and density. So, in the oceanographic charts you will find these water masses, and horizontal flows horizontal flows are stronger than vertical flows. So that is why in any ocean engineering calculation, whenever we say current, so this is the horizontal current. So we don't consider the vertical current, or rather we are more influenced by the horizontal current. So in oceanographic studies or ocean engineering, you have to calculate how much is the strength of the current, and from this we calculate the current force. So current force has to be calculated from current velocities. So this we will find out how we do this later on. And this whole thing varies with depth. So we are more interested in calculation of current from that is the force of current from current velocities. This varies with depth, and normally if you go into more complex calculations, you have to derive these forces from what is called a current spectra. While this spectral analysis is more complicated, right? We are not much bothered about this. Anyway, so this is of the order, the magnitude you can write magnitude of horizontal pressure difference. So this is 1 decibar, that is 1/10 of atmospheric pressure. Now this extends over hundreds or even thousands of kilometers. Whereas in the vertical force, this is mostly balanced by the weight of water, so hardly you will find vertical force, but this actually is the main driver for horizontal currents. So this is one of the aspects of pressure. Now the other parameter is temperature. So what does this ocean temperature do? So it is density defining parameter. So temperature changes density. Temperature of course is directly proportional to your heat influx. When we have more heat, obviously the water will expand, and in the colder regions it will become contract, it will become. So, in the colder regions density will be more rather than in the equatorial region. So, temperature is a density defining parameter. Now, it is also a defining parameter for sound speed. So, all these are linked actually. It is a defining parameter for speed of sound in the ocean. Because once the water becomes more rarefied because of the higher temperature, obviously there will be difference in density, and this will, that is, the sound transmission of sound is directly proportional to your density of water or density of any medium through which it is passing. So, this is actually taken care of by instruments called sonar. So, sound is an important means of communication beneath the ocean surface or in deep waters. The manner of transmission of sound is a separate study altogether that is covered in acoustics. And more, this is particularly of importance to the warships or naval operations, because they employ all these tactics of warships. They employ tactics of detecting sound. So, detects warships sound detection is very important. From the point of a stealth. So, those of you who are going into the Navy or interest in warship design, that means they have to figure out the sound signature of the ship. Sound, and basically the stealth properties comes from, there are two aspects of stealth. Sound, how can you detect anything in the ocean? One is by sound and other is they detect it by heat or infrared radiation. Anyway, so this let us not go too much into detail of this. Now, defining parameters for speed of sound. So, temperature is directly influencing your density, and because of change in density it influences your sound propagation. Now, temperature difference in the ocean is also quite large, as we have seen that the difference in pressure can be as high as how many, 10,000 decibars, isn't it? From 0 to 10,000 decibar is the variation in pressure. Temperature difference in the ocean. So, whatever is happening in the ocean is on a massive scale. So, this varies from below freezing minus 1.7 degree centigrade. Now, this depends on salinity. So, this mostly you will find near the Arctic and Antarctic region. Now, in the tropics, so mostly in Arctic and Antarctic regions. So, temperature is below freezing, that means there the salt there is a lot of salt in the water. Now, this can go high to 30 degrees centigrade, 30 degrees centigrade to 31 degrees centigrade. This you will find where? That is tropical ocean. So, you can see there is also a large difference in the, this is called a temperature gradient. There is a horizon temperature gradient in the ocean. Both the horizontal as well as in the vertical direction. So, this changes your density of the ocean. Now, coming from temperature, temperature is, the difference is in temperature is because of heat. Now, heat, the ocean is deriving from, I have talked about this in your earlier class, from solar radiation. So, that is called insolation. Now, how to measure this heat or heat transmission from the ocean? From ocean, rather you write ocean surface. So, the equation is the quantity of heat, that is normally you will find in British thermal units. So, this is your rho is the density of seawater, and you have to find out the specific heat. Cp is the specific heat and T is your temperature in degree Kelvin. Now, this Q is denoted as heat per unit volume. Rho is seawater density. Cp is specific heat. Now, in this equation, heat is not expressed in British thermal unit. It is heat, quantity of heat is expressed in joules. Q is expressed in joules. That is your unit of energy. Sorry, I was wrong. This is not in British thermal unit. It is expressed in joules. And rate of heat change with which we are interested. Rate is expressed is this is in watts. Now, what is the unit of watts? This is 1 joule per second. Now here is a small problem by which you can find out the heat. Or sometimes in oceanography they call it heat flux. Heat flux is the favorite name given to the heat transmission from the ocean. And this is measured per unit time. Heat flux is given in watts per meter square. So heat flux of ocean, or rather you can say ocean waters. Now there is an example. Calculate heat flux, or rather calculate heat loss. Now from a 100-meter thick layer of ocean, waters. Is needed to change temperature by 1 degree centigrade. So temperature change is 1 degree centigrade in 30 days. So that is, let us take the spread to be 1 month. So calculate heat loss from a 100-meter thick layer of ocean water is needed. Of course, you can strike off to change temperature by 1 degree centigrade in 30 days. Now you use the previous equation. Now your first you calculate this. So let us have a graphical look of the volume of ocean water. So how much is the depth? So depth is 100 meters, and we have to calculate over this heat flux is what are the units? Units is given in watts per meter square. So you calculate the volume of heat that this this volume of column of water is given. So this is 100 meters. And this dimension is 1 meter. Followed. So what is the volume? So volume of this is 100 meter cube. Now in that expression for Q that we have written down just now, so that is given per unit volume, isn't it? Yeah, Q is expressed in unit volume. So you can write the the problem we have to calculate in 30 days. So, per second, how much it is the rate? So you calculate delta Q. Delta Q will be rho Cp. Now both are, this rho and Cp are both are constants. Your delta T is how much?
1 degree.
So 1 degree multiplied by, you have to multiply it by V, that is the volume of this column of water, and divide by the time interval, that is delta T. So this is your formula. So heat change, you calculate heat change, how much it is coming. Now in this equation, you take rho, that is the density of seawater. This is 1025. This is 1025 kg per meter cube. So this is your mass per meter cube, right? And the specific heat, that is Cp, is given as 3850, 3850. So this is your 3000 joules. This is given in joules per kg degree centigrade. Now your equation is dimensionally right or wrong? You first check that. Now V is the volume given in V is we are getting V as how much? 100 meter cube, and delta T is 1. The capital T, that is your change in temperature. What is the change in time? That is your small delta T. So the change in temperature, that is 1 degree centigrade, is occurring in 30 days. So per second if you do, so you divide by delta T. So this will be 30 into how much? 1 day is how much? 24 into 3600. Okay. So now you calculate. So delta Q, if you calculate this heat flux, it is coming as 1025 into 3850. This is multiplied by 1. Volume, how much we are getting? That is 100. So divided by 30 into 24, this is into 3600 we are getting. This is delta T is given in seconds. And this, if you have a calculator, you can work out. In my calculation, this comes to 152.25 watts. So it is not pretty small, isn't it? Your 100-watt bulb, more than your 100-watt bulb. So this is happening in what period of time? Per second you are getting. So this is, the units will be this is passing through 1 meter square, what we have calculated is per meter square. So, this is 152.25 watts per meter square. So, now imagine how much of energy the water is trapping. Anyway, so this is the heat, is a problem with the heat, and next is the salinity part. And if you look at this diagram of this, I have already given the graphs, that is your pressure change. Now, salinity is actually linked with conductivity. Why? Because of presence of salt, and this salt is actually KCl, not is not given. I think this is NaCl. Yeah, NaCl. Now, salinity, this is measured by in parts per thousand. Now, on the layman's definition, this is grams per kilogram of seawater. Now, there is a lot of controversy regarding this. So, now the present tendency is to denote salinity in what is called PSU. If you look into your oceanography book, this is called practical salinity unit. So, normally you will find in the literature they write like this: S is equals to 35.000 PSUs, that is called practical salinity unit. Now, this is based on, there is a parameter called chlorinity. We will not go into the details of this, just for your knowledge I am telling you. The salinity is expressed in terms of chlorinity. So, this is roughly 1.80655 times chlorinity. So, the present convention is to denote salinity in terms of chlorinity of seawater. Now, coming to the diagrams which we had discussed, and this salinity and chlorinity, they are also linked with another term which is called conductivity of seawater. So, this is because of the presence of salt. Because of presence of what? So, seawater is ionized to a large extent. Now, because of this, you get conductivity, that is, can conduct electric current. So, be careful. So, if you look at the graphs, you get like this. These are given you to some extent in your earlier class. Now, this is the pressure. So, pressure variation 5000 here is given. Pressure variation is also 0 at the surface, and your temperature is given from 0 to 20. So, this is somewhere around, this is 5, this is 10, 15. The same nature of the graph will come here, that is your surface zone, pycnocline, and then it becomes more stable after 5000. Now, here also you will find there is another graph called conductivity. The variation in conductivity. Now, conductivity, the unit is inverse of your units of electrical resistance. So, this varies from conductivity variation scale. I think this is given with pressure. So, pressure variation is, this is 1000, this is 2000, say 3000 will come somewhere here, 4000 and 5000. Same scale you take as pressure variation. Only conductivity variation will be, say, 30. This is 35 and this is around 40. You will find that it is nearly the same graph with a slight curvature at the bottom. This is 30, 35, 40, and conductivity is expressed in what are the units? It is in, I think, in this case is micro or micromos. Electrical resistance is measured in ohms, OHMS. So, just invert it, so it will be mhos. And now the salinity. So, the average thing we can get the conductivity is around 35. Anyway, so the salinity gradient. Now, conductivity is actually used in ocean engineering purpose. Can you tell me how you can use to your own advantage? So, 0, this is coming somewhere around 5000 we are getting. So, average salinity is how much? So, average salinity you will get 34.7. So, this is 34 and somewhere this is 34.5. So, this is 33.5. So, this is 34 and this is 34.5. So, I think this will be the reverse of the other two graphs. So, this is a variation of salinity. Now, the last one, now salinity, yes, I told you where it is used. Now, this conductivity of seawater because of salinity is used in what is called corrosion protection. Of underwater part of ships and offshore structures. Now, I am not going to details, but if you ask your professor who teaches you ship production, there are two types of system you will come across. Number one is by means of sacrificial anodes. That is, your zinc anodes, they get corroded, and the other is by what is called a impressed current system, where you take help of the conductivity of seawater. So, these are the two methods of corrosion protection of the underwater hull of the structure, impressed current system. So, next class I will tell you about what is this, what significance you are having because of density. Or variation of density, and how it is expressed, what are the units. So, after this we will go to calculation of waves. Okay, thank you.